In the last decade, with the increasing strain on the world's supply lines, shipping vessels have doubled in capacity and are continuously getting bigger to accommodate a larger demand for logistics. While the ships get larger, the ports remain largely the same, with little capacity for growth or renovation. Thus, in recent years, much research and discussion into finding alternate ways to manage and improve maritime shipping ports has been made. A big talking point amongst the industry now is the use of 5G and beyond 5G technologies to drive innovation in this space. This technology opens the door to a large variety of possibilities, especially in the realm of automation and also brand new emerging technologies such as extended realities. However, this technology is still in the process of maturing. In this video, we talk about the problems faced by maritime ports, what is 5G and beyond 5G technology, examples of how this can be used to implement smart ports to improve maritime shipping and logistics, and potential changes to the OSI model to accommodate these changes.
Ports face a variety of problems during their operation life cycle. One such problem will be port congestion, whereby the logistics is not able to keep up with the numbers of ships going in and out of the port. Other than that, ports also possess a workforce problem, where human workers face a high risk of equipment accidents, which involves large containers and trawling winches. Additionally, ports also face the problem of environmental sustainability, as ports produce large volume of carbon dioxide on a daily basis due to the large number of ships operating within the port.
Now let's talk about what is 5G and B5G. 5G is the latest and the greatest in cellular technology, with B5G or beyond 5G being the bridge of the gap between 5G and 6G further down the line. 5G is built upon three main pillars which essentially defines what it is and how it differs from the previous generation. Number 1. Enhanced Mobile Broadband or eMBB, which basically means that 5G is capable of supporting a much higher data rate, which result in very fast potential speeds for users reaching peak of 10 GB per second and beyond. This will enable new use cases such as extended reality technologies. Number 2. Ultra Reliable and Low Latency Communication (URLLC), which means that 5G is capable from much lower latency and higher reliability. This means it is now capable of supporting use cases such as remote surgery and autonomous vehicle, for example, which rely on these principles. Number 3. Massive Machine Type Communication (MMTC), which aim to allow connectivity for a massive number of devices, which helps to support the Internet of Things. And MMTC also allow devices to intermittently communicate with one another, further supporting the Internet of Things.
Now moving on, we will now go ahead and discuss some new use cases or technology that is enabled using 5G and B5G technology. 5G will allow us to be able to solve environmental sustainability problems, as emissions are beginning to be one of the largest problems in this new era. One such example is through the installation of mobile sensors on barges that can help to measure emission levels of carbon dioxide within the port and the surrounding area. These sensors can do multiple things at once. For example, they are able to provide real-time data regarding the emission levels of carbon dioxide, and also able to provide asset management, whereby the sensors can help provide the location of barges to the port management. There are plenty of reasons as to why we would use mobile sensors on barges. One of them being the large data sample space that can be used, as barges are moving around the port frequently during operation hours. Other than that, it will be significantly less costly to install mobile sensors on barges, as barges are already an existing asset in ports. With all that being said, 5G is the technology which will allow all of this to work through the usage of both multi-slice mobile terminals and multi-connectivity mobile terminals. For multi-slice mobile terminals, they are essentially a device which can be connected to multiple network slices at once. What is a network slice, you ask? A network slice is a virtual network that is on top of a shared domain, which can only be done in 5G. Moving on, multi-connectivity mobile terminals is built upon software-defined radio terminals and small form factor PCs, and utilizes components such as two Intel NUC computers, which are essentially really small computers, and universal software-defined radio platform devices, which allows for radio frequency processing. This software-defined radio platform is able to support upper layer 5G protocol stack and proprietary features that enables multi-connectivity in combination with data duplication, allowing for mobile sensors to be connected reliably at a distance of about 8 km over the air with the utilization of amplifiers and antennas. These two terminals will then be installed in a barge respectively, along with the sensors to measure emission levels. The way this system works is through multi-connectivity, whereby a barge labeled Cell 1 will be connected to a master base station. Once it comes close to another barge, which will be labeled Cell 2, it will establish it as a secondary base station. At one point, Cell 1 will be closer to Cell 2 than the original base station, causing the roles to switch, whereby Cell 2 will become the master base station and the original master base station will turn into a secondary base station. While this is all going on, data regarding emission levels will be transferred between each station.
The second point that we can discuss is the use of extended reality in smart ports. Extended reality is a catch-all term to refer to augmented reality, virtual reality, and mixed reality. Nowadays, extended reality is becoming more commonly used due to the pandemic, which drives more people to commit in virtual activities. Some ways of using extended reality in building smart ports are using virtual reality to get a wider point of view of an area, operating cranes through a VR handle and a headset that provides a 3D virtual environment of the port, helps to train the workers in a virtual environment, and projecting a sample layout of the port city with augmented reality. The benefits of using extended reality in smart ports are: it is convenient, it can help to save materials, for example, substitute paper manuals with digital ones, it has high productivity, it also promotes flexible cooperation between workers, and last but not least, it has a lower chance of accidents happening, as most of the jobs will be done remotely instead of on-site. With 5G and beyond 5G as an enabling technology, XR devices will have a faster connection speed and a lower latency, which many VR AR applications needs. This will also eliminate delays in transmitting data, as 5G uses network slicing. It will also allow logically independent networks to be created on a general physical information infrastructure. Along with support for such high speeds, it will also help XR related apps to be able to stream at 4K 8K quality.
The next idea we have added to discuss is the use of digital twinning in smart port cities. Digital twinning is a virtual model used to simulate, design, and reflect the real object from reality. With the gradual advancement of technology, digital twinning has been widely used in many sectors, such as manufacturing, construction, seaport, industrial, utilities, and other sectors. Digital twinning can provide many benefits for smart ports. Digital twinning can make it easier to better manage port assets by way of adapting, thus reducing the workload for staff as well as reducing environmental impact by improving efficiency of port operations. Additionally, it can also make port a safer place to work as its capability can help to prevent accidents. Moreover, which application of digital twinning can be applied to the entire logistic network for the seaport, and it will be easy to make predictions and autonomous decisions on their assets and inventory from the port. This technology can simulate the whole construction of the seaport and the whole process of the operation through digital twinning technology. Not only that, it will also virtualize the structure of the seaport, real-time status, coordination of management, and much more.
The next point we can discuss is the use of drones such as UAVs and smart ports. In this day and age, the drone industry as a whole is very mature, especially when it comes to the hardware side of it, with hundreds of thousands of individual companies working to develop these flight platforms. Therefore, currently, these flight platforms have evolved to be able to adapt and carry all sorts of payloads which help drones to do all sorts of tasks. Some uses of drones can include, but are not limited to, port security, port monitoring and area situation awareness, emergency response and rescue, inspections, predictive maintenance, asset management/tracking, and so much more. With all this, drones can help make port operations safer, more efficient, and sustainable. Drones can help to prevent incidents from happening. One such example of an incident in recent history is the Suez Canal incident, where a cargo vessel had collided against the bank of the narrow canal, thus getting wedged, blocking the canal and disrupting one of the world's most crucial supply lines and affecting global economies. Drones could have prevented such an incident by automatically tracking the position of the ship in relation to its surroundings by using technology such as AI-powered computer vision. Using this tracking data, it could greatly reduce response times when taking action, potentially avoiding the disaster altogether. Today, such missions are launched through pre-planned timings and routes in today's technology climate. However, with 5G and B5G technology, we believe that it opens up more opportunities for automation, especially with the use of AI systems. The current available computational capabilities aboard drones are not sufficient, primarily due to weight limitations. This is where 5G and B5G can be the enabling technology due to it being much quicker with 100 times higher bitrate and 5 times lower latency in comparison to 4G LTE, which is currently used. With this higher data rate, drones can make use of computational offloading, where UAVs can relay information back to a base station for it to be processed before information is relayed back, which is useful for AI-oriented tasks, which is another big driving factor in the current technological innovation, allowing technologies such as drone swarming, for example. With AI, swarms of drones can be flown automatically, safely, and reliably, all of which communicate with each other and work in tandem to achieve common goals or personal ones. This will make use of the three pillars such as EMBB and URLLC as discussed earlier.
Moving on, I would like to talk about some additional use cases on how 5G and B5G can assist with automation. Firstly, there's automatic container detection and identification. Camera and laser sensors can be used for container monitoring, where the identification of the container number can be achieved by camera and the location of the container in an automatic guided vehicle, in short AGV, can be determined by a laser sensor. This will improve visibility by providing detailed data about inventory, orders, vehicle routes, and other aspects of a port's operation, thus improving the warehouse logistics and inventory monitoring. 5G and B5G will come in handy in this scenario, as 4G will soon be insufficient for places like smart ports, where more and more things are being automated, which will result in much more data transfer. Furthermore, 5G and B5G can also be used to improve communication systems at the ports. This is because, as ports contain many metal-made containers and machines, communication signals can be bounced off of the metallic surfaces, which can result in the signals being deteriorated greatly. To solve this, with the beamforming characteristic, 5G and B5G can send their wireless signals in a specific direction, which allows the targeted receiving devices to obtain the signals in much greater condition, which makes them much more ideal as compared to 4G, which broadcasts its signal in all directions. Moving on to the next use case, AI analysis to decrease risk and improve cargo ship routing. AI that studies and analyzes prior accidents can suggest ways to prevent potential similar future accidents from happening again. For example, having sensors around ships and ports to collect data for analyzing and forecast weather in the future more accurately, to which this will need the help of 5G or B5G, as 5G sensors will be able to directly enable vast data aggregation for remote monitoring and immediate reaction. And with this, AI can also help in calculating the best optimal routes for each cargo ship or taking the forecasted weather information, traffic, type of cargo ships, destinations, etc. into account.
In this section, I will discuss regarding potential revisions that would have to be made in regards to port architecture in order to better support 5G and B5G technology. One way B5G technology can enable the building of smart port cities is by further extending the range of frequencies of signals in which data can be propagated into the sub-terahertz range. Despite how recent 5G mobile networks have been implemented, the frequency spectrum offered by 5G networks, which is up to the millimeter wave range, is already reaching saturation, with more devices having wireless network connectivity and more data being transmitted wirelessly over the network it is connected to. In the case of smart port cities, machinery will be transformed into IoT machinery to accommodate remote operation and monitoring. Furthermore, accessories that would be used in the smart port city, such as AR glasses for viewing the contents of shipping containers, would contribute to data traffic. Increasing the frequency range will not only allow more radio waves to be transmitted, but communication channels will also widen, giving rise to increased data rates. Additionally, higher frequencies equate to smaller wavelengths, allowing transmitters and receivers to be downsized. The biggest issue in extending into the sub-terahertz range of radio waves is the path loss of the signal as it propagates through space. Radio waves innately already lose power as it travels a further distance, with this loss being further elevated by factors such as absorption into the medium the signal is propagated, physical obstacles like buildings, diffraction effects, and superposition effects. In addition to these natural effects, increasing frequency also increases the path loss of the signal, since phase noise and power amplifier distortions increase as well. A port city in general would be full of obstacles to radio wave propagation, and with obstacles such as shipping containers and machinery constantly moving, there is no one fixed physical port architecture to design the physical network architecture around. A port city is also subject to weather conditions, which adds another degree of instability and uncertainty to the higher frequency signal. This will be highly detrimental if an essential or a critical function in the port requires communication through higher frequency signals.
Moving on, now we're going to talk about the OSI model. Networks are designed using the OSI model, which consists of 7 distinct layers designed to separate the complex tasks of networking into multiple more manageable ones. With this, there are some changes that we believe that can be made to some of the layers in the OSI model in order to help better accommodate 5G technology.
Signal transmission takes place in the physical layer or layer 1 of the OSI model, and thus the solutions to implement extension into the sub-terahertz range can be found in this layer. To address both the limited distance that sub-terahertz signals can travel and the poor ability of sub-terahertz signals to navigate around obstacles with minimal distortion, 3D beamforming can be applied throughout the smart port city. Beamforming is a technique which can adjust the amplitude and phase shift of incoming signals. Present beamforming techniques can only control beam patterns in a horizontal plane. However, with current research into reconfigurable intelligent surfaces, or RIS, it will be possible to beamform in 3D. RIS is composed of numerous passive reconfigurable elements that are able to control the amplitude and phase shift of incident signals, effectively beamforming the signal in 3D. Technology such as RIS essentially extends the coverage of devices, proving to be a valuable hardware in the implementation of sub-terahertz waves for the building of smart port cities. In addition to the limited distance sub-terahertz signals travel, extending into the sub-terahertz range of radio waves will introduce more signal interference between signal transmitters. To address such, massive MIMO or MMIMO systems can be deployed to break past the limit in the densification of signal transmitters. Interference, fading, and noise power are reduced with the increase of wave antennas in MMIMO systems, making these systems capable of achieving massive MIMO gains while being passive and only requiring a limited number of active antennas without compromising quality of service. MMIMO systems can also be made to be more efficient and scalable. Hybrid precoders will replace digital and analog precoders in an effort to reduce the energy consumption of MMIMO systems. MMIMO systems do, however, have the issue of security in the form of secrecy rate. Researchers propose maximization problems to maximize secrecy rate subject to quality of service constraints to improve security.
A proposed change to the OSI model which may help accommodate technologies that use a large number of moving devices such as drones is an introduction of a new sub-layer in the OSI model in between the network and data link layer, which would be called the topology control layer or layer 2.5. Its main purpose would be to allow drones to broadcast its position information obtained via GPS to determine relative positions in a swarm. This new proposed layer can obtain the positions of 4 neighboring UAVs and figure out a routing algorithm and create a routing table for the data to be transferred back to a base station. In addition to this, it can also designate an appropriate transmit power for each particular link, thus making the whole process a lot more efficient and also reducing background radio frequency congestion, thus improving and being a benefit over using traditional fully connected topologies. This helps to optimize the power that is currently untouched by the other layers.
The network layer is the third layer of the OSI model that handles the service requests from the transport layer and further forwards the service request to the data link layer. It determines the route from the source to destination, but it also deals with problems such as switching. Packet switch networks such as 4G and 5G are implemented at the network layer, which brings us to our point. In both 4G and 5G, timing and synchronization are fundamental for them to function, as this helps to prevent signals from interfering with each other whenever a device switches from one signal source to another. This helps to ensure reliability of the connection, thus in both network standards, the timing, frequency and phase have to be in sync. However, due to the high tolerances of 5G, it has much stricter synchronization requirements. An example is that it can only tolerate a sync margin of 1.5 microseconds. The way this is commonly done now is through GPS satellites as a primary source of primary time reference clock or PRTC. However, this can be unreliable as it suffers from coverage issue due to obstacles, for example in which there are a lot of imports or even events such as leap years, for example. One way this limitation can be mitigated to help fulfill the requirements of 5G and future B5G is the use of a ePRTC or Enhanced Primary Reference Time Clock as defined by the ITU Telecommunications Standardization Sector, in short ITUT. This technology makes use of highly accurate timekeeping devices such as cesium clocks to keep their own time in combination with GNSS receivers. This allows them to maintain accurate timing within 100 nanoseconds for at least 14 days, thus removing vulnerability to GNSS outages. This combination of technologies leverages the advantages of both to improve accuracy and reliability of the connection.
In conclusion, we believe that 5G and future beyond 5G technology can bring a wide variety of benefits for ports, transitioning them into smart ports. This all can be done primarily by automating a bunch of tasks in ways that would originally be impossible. With this, there are however changes that can be made to the OSI reference model that we believe can help accelerate the transition to make smart ports a reality. Thank you for watching this video, and see you all next time!